So welcome everyone. So today we have a sort of a special topic. So Andrew Craik and Eric Ochoa is going to talk about some inlining technology that was under development as a research project with the University of Alberta, and the intention is to contribute that to OMR if possible. So the purpose of today's meeting is for Andrew and Eric to basically take us through the technology there, and for us to understand the best way of integrating that within OMR. So I'll turn it over to Andrew, who's got some slides.
Yep, and they should be on the share for anybody who's looking at the WebEx. So thank you for the introduction, Daryl. So I'm going to do pretty much most of the talking today. This work is a joint research project between IBM and the University of Alberta, and the heavy lifting on the implementation, as well as a lot of the innovations in how we do some of the inlining and stuff, is work that Eric Ochoa has done as part of his master's thesis at the University of Alberta. Eric would normally be presenting, but he's in the throes of writing up. So I volunteered to do the talk just so he had one less thing to worry about. But he's on the call and will be able to answer questions and correct me if I get anything wrong. So I'd like to start just by sort of sketching the current state of the compiler. So if you look at what OMR has at the moment in the way of inlining, there is one inliner. It is called the trivial inliner. It's a very basic inliner that works by inlining a limited amount of small methods. So it has, sort of a budget heuristic, and it picks only small things to inline. It has no real concept of what the best thing to inline is. It just picks small things and inlines them. It's sort of the minimum viable concept of an inliner. It knows how to stitch bodies together, but it doesn't know much beyond that. Now, OpenJ9, which was kind of the other part of the IBM Java technology that got open sourced, has a massive and complex inliner that's called the multi-target inliner. That's being developed over the last 2 decades. It's very Java-centric. It's full of heuristics. Its operation, it does a form of guided eager inlining with some backtracking in what it's doing. It can miss opportunities because it does tend to go in a depth-first manner and has a budget, so once it's used up, if it hasn't searched a particular path, it won't even be considered. It has a single metric that it uses to judge the worthiness of inlining something, and that means that it can conflate a small method with a low benefit and a large method with a large benefit, because the division will kind of result in the same answer. And you don't have a good way of choosing between them. And the code is relatively convoluted just because of all of the development that's happened over time, and it's a bit hard to reason about and control the inlining in some circumstances in there. So obviously this is not ideal for the OMR project. So when we sat down to start doing this project, our question to ourselves is, how can we do better, right? If the one in OpenJ9 isn't one that we could generalize into OMR nicely, and the one in OMR isn't that smart yet, how could we build a better one? If you sort of start from first principles, inlining provides a number of benefits to the optimizer. So it reduces function call overheads when you're executing the program. You call less stuff. And it provides improved opportunities for optimization. By amalgamating code units together, you can discover facts that you cannot discover looking at them in isolation, and therefore you can do better things to the code to make it go faster. Now, inlining can also have negative effects, right? If the method gets too large, it can be hard for it to be easily compiled. You may run out of resources, or the time complexity of some of the optimization algorithms may become a limiting factor on being able to do something useful with it. And inlining the wrong things can have an adverse effect on hardware behavior, right? If you inline lots of stuff, but it's not stuff that actually runs, you're going to reduce the locality. You can have all kinds of other negative effects. Now, if you look at the current state of the art in inliners, not just in OMR and OpenJ9, but sort of across academia and across industry, most of these, pretty much all of these inliners are guided using sort of a single metric. So you have a budget of some kind, and you choose candidates to inline until you fill your budget, right? So a standard knapsack packing problem. Now, you guide the inliner by inflating and deflating that metric, right, to make things look more or less attractive. But in all of these cases, size and opportunity for optimization are conflated, and it's very difficult to achieve optimality because of that conflation. So in setting out to try and look at doing a new inliner, which was kind of the goal of the research collaboration that we had, we wanted to separate the notion of cost and benefit, right? So a cost is the amount of space or the amount of instructions or whatever that you're willing to grow the method to, your budget. And the benefit is how much better we think the program will be by having inlined that method, right? So it's a measure not only of saving the function call overheads, but also the opportunities for optimization that inlining can unlock. Now, benefit also necessarily needs to include a notion of relative execution frequency, right? So if cost is just the size of the thing, having execution frequency factored into the benefit makes sense, because if you have two things with equal optimization opportunities, the one that's more frequently executed is the one that you want to inline, right? And we want to make the inliner guidance in the new implementation much more scientific. So if you go and look at the multi-target inliner, some of its decisions can at times appear rather magical, and it requires some careful analysis of the code to understand why it chose to do what it did. And changing that decision can be tricky. So the basis for this research project, so before this was background work that was that we'd done at IBM before we started this collaboration, was that we developed an algorithm to solve the knapsack packing with dependencies problem, right? So the standard knapsack packing problem, right, you have a backpack of a given size, you have objects of various sizes or weights, and you wish to fill the backpack as full as you can. That is a solvable problem. It has well-known algorithms in the literature. Now, if you add dependencies between those, so you can only include A if you've included B, for example, there are very few algorithms that can solve that problem. So what we developed was an algorithm to solve that problem. Now, this algorithm has not been formally proven to be optimal in all cases yet. But in practice, it does produce optimal solutions. So we fed it quite a lot of different problems to solve, and in the case modeled off of sort of inlining, and it was able to solve those problems and produce the optimal result. The algorithm is based on dynamic programming, and it uses 2 layers of backtracking to allow de-optimization during the search to help you find the best inlining solution, right? So what I'm going to do is just run very briefly through how this algorithm works, just so you get a flavor of how this knapsack packing problem is solved, because it's sort of intimately tied into the representations we've chosen for the new inliner and how the new inliner we've built operates. So the fundamental currency of this algorithm, or the fundamental data structure behind this algorithm, is something that's called the inlining dependency tree. So this is derived from a call graph, but the thing that you need to note is that each node is call site specific, right? So in this example here, we have A calls B and C, so you have A connected to B and an A connected to C. C calls E and F, so you connect them. If A were to call B twice, there would be 2 B nodes as children of A, where B1 would represent call site 1, B2 would represent call site 2, right? And so this does form a tree. There are no cycles or acyclic regions or merges. It's strictly a tree in the graph sense of a tree, right? And that has a nice property for doing these searches, which you'll kind of see unfold. So we take this inlining dependency tree and we annotate the nodes with costs and benefits. So the notations shown on the tree in the slide, you have a cost on the left-hand side of the slash and a benefit on the right. So node E has a cost of 1 and a benefit of 7. So therefore, if you have enough budget to inline E, you're probably going to want to inline it because it's the most beneficial thing. There was a question in the room?
So one question, so if there is a recursive function call in the method, will it inline to make the tree deeper, or does it just leave it at?
So in the description of the algorithm as we wrote it, when you're building the IDT, you already are, like, you give this algorithm the budget that you're going to work with. So for recursive calls, the node is repeated as a child of itself out to the maximum depth that your budget can accommodate, right? So
That's all I wanted.
yeah, effectively it does the loop unrolling by representing that.
Yep, got it.
So the costs and benefits here are just the nodes themselves, right?
The nodes themselves, there's no transitive
cumulative
notion.
aspect.
There's no transitive notion, so the costs and benefits are isolated to the node itself, right? And for a given budget, we wish to pick the most optimal subset that we can to inline for this thing. So this thing is a dynamic programming algorithm. It works with a table. It considers the nodes in the IDT in a post-order traversal from lowest benefit to highest benefit at the same level, right? So with a post-order, you'll visit all of the parents before you visit the children. And for siblings at the same level, you will visit the lowest benefit to the highest benefit. And that is just to maximize the number of combinations or number of possible solutions that you generate into the table for each given budget, right? Which is what allows the de-optimization search to work. So we're gonna run this algorithm for a budget of 5, and so we've created a table. We've got 5 columns. Column 1 is the solution for a budget of 1. Column 2 is the solution for the budget of 2, and so on. And we then begin considering nodes in the order that I described. So first we consider node A. Node A has a cost of 1, and for all costs, it's the only node that we've considered, and we have enough budget, therefore we will inline it. Okay. Considering node B. Okay, so node B, when we look at column 1 for node B, we can't inline node B on its own because B depends upon A. So when we go to try and put B in, we have to subtract B's cost from the available budget and then look at the previous solution. If we subtract B's cost from the budget, the remaining budget is 0. There's no way that we could fit it in. Therefore, the solution in column 1 is A. In column 2, we have B. We subtract the cost of B, which is 1, and we look at the solution in the previous row at column 1, which is our remaining budget, which was A. Can we combine A and B? Is the solution valid? Are all of the dependencies of B included in that set so that we can graft B onto it? The answer is yes. Therefore, the best solution so far at budget 2 is AB, and that holds for the remainder of the columns. Right, so it's this looking at the previous row, which is what these arrows indicate. Node D, a similar operation happens. Column 2, you have AB because there is no way to fit D in, right? If you go and consider D, and you look back at the column 1, right, taking 1 off, you have A. Well, you can't have AD. So then I would have to consider D and its predecessor, B. So now I want to inline BD. The cost of that is 2. That uses up all of the budget, so there's no way to possibly inline BD, right? So the best solution at 2 is still AB. At 3, when we look back at column 2 in the row before, AB is there. We can graft D onto that without violating the dependency, so the solution is ABD, right? Now, likewise for C. Now, the more interesting one is then when we consider node E, right? So look at the last row, row E, and look at column 3. So we begin by considering E, which has a cost of 1, and we look back at the row before, AB. Well, we can't graft it on there, right? The dependency C is not included in that set, so it's an invalid solution. So then we include its parent. So now we're wanting to consider inlining CE. We consider CE and compare that, right, with, sorry, that should be pointing at the row C, not the row D. It should be looking at A in column 1, and you end up with ACE as the solution, right? And this shows that we've actually backtracked, right? The thing that's interesting is you look down column 3, and we decided when we'd only considered up to C that we wanted to go ABD, which is down one side of the tree. The backtracking has undone both of those decisions and now selected ACE as the path to inline. Right? So this is one of the backtrackings in the algorithm. The other one has to do where there's an overlap. So if you had, say, AC as a solution and you wanted to graft CE, you end up finding out, oh, well, there's an overlap. That overlap indicates suboptimality, and then you continue backtracking up that column. So there's these other ways of grafting the solution.
There's absolutely no implication in terms of the ordering here, right? These are just distinct nodes. You're saying this is what belongs in the set.
This is what belongs in the set. So it doesn't say anything about the order in which they should be inline. It's just the set of things to inline.
But because there's only one edge ever coming in,
yes,
it's kind of implicit where it's going.
It's implicit where it comes from, right? You can derive it just by having the set of nodes, right? And because it's a tree, you know you have to inline anything, you have to inline the root, and then the rest is paths from the root to the various nodes, right? Which may pass through things in the subset, right? But none of the paths that are in the solution will pass through a node that's not in the solution, right? You have to be able to inline every node along a path.
Okay, so if a node is there in the solution, every node from the root to that node will also be there.
Has to be there because of the dependency part of the algorithm.
Right.
Okay, so that's the basics of this algorithm. That's the basics of how this algorithm works. This was an input to the research project. So this was formulated sort of in isolation with the idea that it would be useful for inlining, but we hadn't actually built an inliner that used it, right? And we'd had an implementation in Python that we'd used to prototype this. Now, in this, I had cost numbers and benefit numbers. Now, cost numbers are kind of a relatively sort of straightforward thing to have some kind of intuition as to how to derive, right? It'll be a measure of the number of instructions in some way, right? It could be the number of instructions, say, in Java bytecodes is the thing that you're planning to inline if you're doing inlining for Java, or it could be the number of nodes in the tree representation of a method that you're planning to inline. It's just a cost of the cost of inlining, right? Like how much this thing is worth, right, in terms of code size. The thing that's a lot more magical and was left as sort of an unknown in the design of this packing algorithm is how do you derive the benefit? What is the benefit number, right? How do you cook that up? And that's really where Eric's research picked up, was trying to figure out how to build a benefit number, right? So how to compute the benefit? Well, there are really two components that we want to consider in the benefit, as I sort of stated earlier. We want to consider the frequency. That is, if two things have the same cost to inline, we wish to inline the one that is run more frequently, because we will save more in terms of the call overheads. And the other one is optimization opportunity. If two things have the same hotness, same execution frequency and same size, we would like to inline the one that is going to provide more opportunity for the optimizer to optimize it, because you will end up with a program that runs faster, right? So in the formulation that Eric has, the frequency of a call within a method, so we have to derive a frequency ratio, right? So the ratio is derived as the ratio of the method entry frequency to the frequency of the call site. And in Java, we're doing this just with the standard profiling infrastructure that we would normally use to set block frequencies. So the APIs for doing that are APIs that already exist in OMR. That ratio can be calculated. It's calculated for a single call, right? So it's a single node, and so you can get a multiplicative factor if you follow a path, right? So, you know, if going from A to B is 10 times hotter, but then from there you go to something that's cooler, you get a fractional multiplication, and the whole thing kind of works out as you do it transitively across the tree. So that's kind of how the frequency part of this works. Now, the real question is, the real part of this research and what Eric has spent most of his time on, and where he's made a lot of some great innovations, is the opportunity for optimization. Essentially, we want to model which optimizations may be unlocked by the inlining of a method, where there's information from the caller that will allow the optimizer to do something good in the callee that we would not have been able to do in isolation. So the idea that Eric adopted and ran with was to run an abstract interpreter over the program representation, computing symbolic values or constraints on values so that we can model what we know about values in the program. So in his current implementation, this is an abstract interpreter over the Java bytecodes. We chose the Java bytecodes because in the context of OpenJ9's use of OMR, the generation of trees is expensive. It consumes a considerable amount of memory and compile time. And so writing an abstract interpreter to traverse the trees, well, we would necessarily have to generate the trees in the first place, which was prohibitively expensive. Now, you could do it over trees, but for reasons of efficiency and comparability to the existing inliner, we did it over the bytecodes. So this abstract interpreter is run starting at the root method, and you start constructing constraints on the values. And when you get to a call, you will begin interpreting the callee. So you take the callee in isolation and you will interpret that callee. And what you're trying to do in that interpretation is to find the opportunities for optimization. Now, these are done sort of as pattern matches in terms of the operations that are being seen. We've got some examples of the ones that are currently looked for. When we see one of those opportunities, we want to record the dependency of that opportunity on the parameters of the function. So if say you're going to do branch folding, right? One side of the branch is a constant. The other side is an expression that is dependent upon on an input parameter. We can derive a constraint that says, well, if the parameter has between value A and value B or is equal to value X or whatever, then this branch could be folded one way. And if it's constrained in another way, we could fold the branch another way, right? And so what we will do is record those in a table, and we store that as a summary. So what you end up is a summary of potential optimization transformations and constraints in terms of the parameters that will allow that opportunity to be potentially realized. There's a question in the room? Yep.
Yeah. So when you say constraints, how is that related in any way to the value propagation notion of a constraint, or is this a completely different constraint hierarchy?
So Eric has recycled all of the value propagation constraints. So it's producing value propagation constraints and using that infrastructure.
So the next question then is, you mentioned something about the act of IL-genning is quite expensive. Yep. I don't know if you meant specifically memory or time or both, perhaps, is what you meant.
Both was what I was alluding to in the context of the OpenJ9 inline.
Yeah. So interpreting and creating constraints.
Yes.
It does incur some overhead as well. Right?
It does, and we have a detailed evaluation for that, which I'll show. We've measured the cost of that.
Okay, but I was saying it does. It has the same feel of walking over bytecodes. You have to walk over bytecodes for ILGen. You have to generate nodes in one case. You have to generate constraints in the other.
Right.
So is that really that much less expensive? And you will. I understand you have data, so I'll wait for it.
If I may just respond on that point.
Yeah.
If we were to do the abstract interpretation over the trees, you would not only have to walk the bytecodes and generate the trees, consuming compile time and memory, but you would then have to walk that representation to generate constraints if the abstract interpreter was written in terms of the trees. We chose to skip that step and do it directly for the reasons of efficiency, but you could build one to work on OMR's tree representation directly. We just didn't do that because of the constraints in OpenJ9 where we were studying.
Yeah, makes sense. So the other question I have is around this particular implementation. It's iterating over Java bytecodes.
Yes.
Is looking for Java opportunities, or is it more general already? Like, I understand the topic here is contribution to OMR.
Yes.
So has that walk been abstracted in some way, or is that the future that you're anticipating?
So the API for calling into the abstract interpreter is defined. Now, in terms of how you would pattern recognize the opportunity that you are looking for, currently those patterns are formulated in terms of the bytecodes because the pattern is implemented in the abstract interpreter, right? So if you were to write a different interpreter, you would have to recognize the pattern that would allow you to perform an optimization. But the optimizations that are being recognized are optimizations that exist in OMR. So they are not Java-specific optimizations. So we're looking for things like branch folding. I've got other examples, right? So they're things that the OMR optimizer is capable of doing, and you could certainly abstract some parts of that from the interpreter. We haven't done that at this point.
Okay, so the capabilities that you're looking for are present in the OMR compiler,
yes,
but the way you're looking for them is still fairly Java-centric.
Yeah, that's fairly Java-centric at the moment.
Okay.
Right.
Okay, thanks.
And so once we've produced this summary table, we go back to looking at the call site, and the call site has constraints on the actual arguments that are going to be at that call site for that particular call. You can intersect that set of constraints with the constraints for each potential optimization, and where the answer is that it unifies and matches and the constraints in the table are satisfied, you can take those optimizations, and those are the ones that have the potential for occurring, right? And we store a benefit metric with each of those potential optimizations, which I'll cover, so you can add those together, multiply them by the scaling factor, and you get the benefit of inlining that particular method at that site.
Straight. So when you pass a parameter in,
yep,
you have a constraint associated with that parameter. You have other constraints that are coming in from the callee. You're intersecting those two, yep, and if something better happens as a result of that intersection, you say there's a benefit.
Well, it's basically if the constraint in the, so you have the method summary table where you have these potential optimizations and the constraints which must be satisfied. So you take the information you have at the call site, and the intersection is to say, does it satisfy this constraint? If the answer is yes, it satisfies the constraint, and it does that for all of the parameter constraints for that optimization, right? Because we have one for each of the parameters. We intersect each parameter. And the answer is yes for all of them. Then that optimization can be unlocked by the information in the caller if you inline that callee, is the intuition.
And this was done for values, integral values, or types as well?
Both. So we've taken, Eric has taken most of the constraints in value propagation and employed them. So the ones that are being used, which is what I have on this next slide, so integers in terms of integer ranges or specific values, strings, so in terms of constant strings, there's representation for that in value propagation, and we use that. Null constraints, objects in terms of constraints on the class type and on nullness, and arrays, constraints on the array size, as well as the type of the element, the element type of the array. Right? So standard value propagation constraints.
I have a question.
Yes.
So the constraints, it looks for them on the parameters you said, right?
Yes.
That's to the callee.
So so there are two sets of things that are computed. So when you compute a summary for a method body, you interpret that body without any context, producing symbolic constraints in terms of the parameters. And when you find an opportunity for optimization that is dependent upon parameters, you record the constraints for each specific parameter that's required to unlock that potential opportunity. That method summary is stored and is independent of the context of the call, right? You've interpreted that method in isolation, produced symbolic constraints in terms of symbolic parameters, and that will tell you that there's a set of potential transformations that if the constraint for that thing is satisfied, the optimization can potentially happen. It's not a guarantee, but it means that the information should be there. So when you encounter the call, you build that the first time if you don't have it. Meanwhile, when you come back to the call site, you have a set of constraints for the arguments at the call site. So it's does the set of constraints that I have at the call site satisfy the constraints that I needed for the particular optimization? And that allows you to filter the set of potential optimizations to a set that can actually happen based on the information that you have available, right? And I need to point out that it's not, you can have false positives and false negatives with this, and that will just mean that you will make inlining decisions that are not optimal because you approximated in some way or had a lack of information. It's not a correctness concern, right? So the precision of this abstract interpretation and whether, say, in a loop you compute a fixed point or you do a single iteration or a multi-iteration or how you do that, right, is a function of how much time you're willing to invest into the abstract interpretation. And you can get a more precise or a less precise answer. The less precise you are, the more likely you are to make a suboptimal choice, but if it's good enough, most of the time you will get a good answer, right?
So can it look also at other things like, say, a field of an object?
At present, no. You could extend this idea of the summary table to include heap objects. Yeah. In the context of what Eric was doing in the time and what we had, we focused on the parameters.
Fair enough. Thank you.
Can we cache the I guess, context-less?
Yeah, so the method summary table is computed once for a method. At the moment, it's computed in each compilation, but in theory, it could be shared across compilations if you wanted to, right? Unless the method was redefined, the summary will remain the same because it's this, you ran an abstract interpreter, which is a state machine over the bytecodes, and produced an answer that is independent of any context in which that method is being called. So at the moment, it's produced per compilation. It could be reduced by sharing, but we didn't want to get into the complexity of the memory management associated with that.
So if you have an opportunity where the specialization spreads across more than one call or deeper than one call, right? Like the parameter, something that you're passing to the parameter to a called method, and it's used in the callee, but it's used in a callee of the callee.
Yeah.
Then you'll catch that as long as at some point in the algorithm you can find a way to inline the first guy.
Yeah.
And then ideally, when you're evaluating the second guy to evaluate, the benefit will be high because there'll be this synergy.
Yes.
But if you can't find a way to inline the first guy, you'll never see the opportunity of that. I'm not saying we do it.
You won't be able to realize the opportunity.
Yeah.
Right.
The algorithm won't be able to find its way into the benefit.
So if you had like a shell method that just passes parameters down, is kind of the prime example there.
Yeah. Well, I was thinking kind of like an interface where you go through a layer and that's where it actually gets used.
Right. So when you, so you can.
But that's not. Yeah. I mean, that's not. Sorry, that's a limitation. That's a current limitation of what you do now.
Yeah.
It's not necessarily a long. It doesn't have to.
It doesn't have to remain a limitation of how it works in general.
Right.
So on the screen, I have one of these sample method summaries. So there's just some examples of branch folding here. So it records a benefit metric for the branch folding, and at the moment in the bytecode abstract, Java bytecode abstract interpreter, it's the number of bytecodes that will be eliminated if that branch fold happens. That's the benefit. It records the location of the opportunity and the constraints in terms of the parameters. So a blank means that we don't need, like that argument is free. We don't need it to satisfy any particular value. A constraint in the column gives you the range that has to be satisfied for that particular opportunity to be realized. We implemented this with the Java bytecodes in OpenJ9. At the moment, the optimizations it models are branch folding, null check elimination, check cast elimination, folding of constant length strings, and some opportunities for partial evaluation, right, where you would be able to do a compile time evaluation of part of an expression because you would have some constants that you could fold away. We've been able to run a large amount of stuff with this. It's managed to run DayTrader and things like that. The data we've produced is for the DeCapo benchmark series. And specifically, I'll show results that Eric's gathered for Avora, PMD, LooSearch, LooIndex, FOP, Eclipse, and Sunflow. Right, so a fairly diverse set of things. Now, each of these benchmarks was run in isolation. So we would start a JVM Eric would start a JVM to run that specific benchmark, so like LooSearch, right? So there was only one thing that the JVM was trying to do. The benchmark was run iteratively, so we would run the benchmark again and again and again to give the JVM and the JIT an opportunity to warm up. What Eric did was measure on the experimental setup the number of iterations that were required for the JIT to reach a quiescent state where the number of compilation had ceased. He added a few extra iterations to that, like 3 or 4, and then we would measure throughput performance as the amount of time to execute the final iteration before shutdown after the warm-up, right? And we were measuring compile time, so the total CPU time consumed by the compilation threads as reported by the vlog. The compile memory, so the total memory consumed during compilation, also from the vlog. Generated code size, as in the number of bytes of instructions generated, also from the vlog, and that was just subtraction of the addresses specified as the range for the method. And the runtime, so that was the time to execute the final iteration after the warm-up period, e.g. a representation of the steady state throughput. So there were 3 configurations in this evaluation. There was a baseline, which is the current OpenJ9 heuristic inliner, the multi-target inliner. The frequency, what's labeled as frequency, which is this new inliner algorithm that we have where all of the benefits are set to 1. And that's basically just inlining based on frequency. And then there's the analysis, which is the new inliner that uses both the frequency scaling and the abstract interpretation, right? So we're adding the cost of the abstract interpretation in the hope that it will do something good, right? The evaluation was done on x86-64 Linux on Skylake. We ran with a fixed heap size, and the heap was set sufficiently large to prevent global GCs occurring during the run. And the machine was isolated with nothing else running on it at the time that the evaluation was done. Okay, so runtime. So all of these bars are normalized to the baseline. So all of the baseline bars, which are the dark blue bars, the leftmost bar is 1. The runtimes for the middle bars, or the orange bars, are for the frequency inliner, and the gray bars are for the analysis inliner, where we added the abstract interpretation, right? And lower is better, right? So if you're running for longer, you'll have a higher score, right? So FOP is not doing as well because it's running slower, right? Xalan, right? So generally, it's roughly on par. There's LUIndex and FOP where it's somewhere between 10 and 20% worse in terms of runtime. Right?
Sorry for asking this, but can you go back to the previous slide again? I just want to make sure I understand the So it is a progression, right? Frequency has more, analysis has frequency plus the intelligence on abstract interpretation.
Correct. Yeah, it's a progression.
Sorry, yeah, go ahead.
Okay, so that's the runtime. So in general, it's on par with the current heuristic inliner. There are 2 outliers where it's not managed to do as well. Note, we were modeling a very limited set of optimizations. So optimizations that may have been important for those benchmarks may not have been modeled. LUIndex, for example, is a very loop-intensive benchmark, and there was no real, beyond the frequency, there was nothing that was specifically things that LUIndex would need. Now, compilation time, again, this is normalized to 1. Lower is better, right? So, for example, LUSearch, it was about, we consumed, the new inliner consumed about 70% of the compile time of the current inliner-based solution. In Sunflow, it was getting up towards 2x the compile time. And I'll comment on that afterwards.
Does this run at warm and at higher opt levels?
All opt levels, cold and up, everything. We replaced all inliners. There's no other inliner other than this inliner running. Compilation memory usage, again, lower is better, normalized to 1. So Avora used 25-30% more memory, but like LUIndex, it was less memory, right? About 90%, 85% of the memory. Generated code size, lower is better. So it's generally producing smaller method bodies, managing to match the performance in a number of cases. There's a bit of difficulty in comparing the baseline inliner against the new inliners because the current multi-target inliner is capable of adjusting its budget at certain points based on heuristics, whereas this inliner is completely fixed. You give it its budget, it's going to stick to that budget. It's not going to increase it or decrease it depending on what it sees. So it can be a bit of a moving target that you're trying to compare to. We tried to get these, as Eric spent quite a lot of time trying to get the sizes as close as possible in terms of budget, but it's certainly possible that there are variations happening that weren't nailed down, right? We studied the topmost methods, but there's still variance that could occur. So I just wanted to comment on a few things from that analysis. So in general, the new inliner is more expensive than the current OpenG9 inliner in terms of compile time and memory. There are a couple things I want to call out. First is that the current inliner does not do a full exploration of the state space, right? It is an eager inliner. It may backtrack at selected points, but there is no guarantee that it will consider every possible inlining combination. Whereas the new inliner, for a given budget, will consider all possible combinations. So the state space that's being searched is larger, which necessarily, in some cases, increases the amount of memory and stuff that's being consumed. The compile time is generally comparable. We had one case where it was sort of 2x, but a lot of those bars were very, very close, and in some cases lower, right? So in general, it's doing fairly well on that. The memory was within 20% of the baseline, and again, considering that it's doing a full state space exploration, some growth is to almost be expected. The abstract interpretation is relatively cheap, right? The difference between the orange bars and the gray bars in terms of the memory and the compile time, right? There's not a significant difference, right? It doesn't cost you that much to run the interpreter. Now, obviously, as you add more patterns or more complex patterns, the cost will go up, but the majority of the cost at the moment is doing the state space exploration with the packing algorithm. Now, the new inliner can produce the same performance with less code. So we saw that with like LuIndex, it produced something like about 25% less code, but it ran at the same throughput. And the runtime performance is generally pretty good considering the number of optimizations modeled and the lack of any Java-specific heuristics, right? The baseline has several decades worth of knowledge of Java and what things are good to do. This inliner has none of that. It was only working based on the frequency and that limited set of optimizations that it was modeling, and it got pretty close in a number of cases to the current inliner. Now, there's certainly a lot of room for this to continue being expanded upon. The research collaboration between IBM and the University of Alberta is continuing, and Kareem Ali, who is Eric's supervisor and the principal research investigator at the University of Alberta on this project, and I have discussed that there will probably be another master's student starting later this year to continue work on this inliner. A lot of the information propagation that I was describing is downward information propagation, so I know something in the caller, I wish to use it in the callee. That's certainly valid, but upward propagation is something that's currently missing and is one of the main things we'd like to explore in another master's. We'd also like to try and model some more complex optimizations. The main one that we have in mind at the moment is escape analysis, because that can have a huge impact on how you choose to inline various things, and we'd like to try and see if we could figure out how to model that. Outside of the scope of the academic research, obviously for consumption in OMR, having an abstract interpreter over the trees would be desirable. It's not something that we currently have, and I don't expect that it would be something that the University of Alberta would produce at this time, because they're interested in the questions around how to model optimization cheaply, how to guide the inliner in a better fashion. That abstract interpreter is more engineering and less interest. We would like to contribute this work to OMR. So the proposal for how to contribute this would be that the core of the inliner would be contributed to OMR, and that would be the knapsack packing algorithm implementation. That would be the all of the code for basically doing the unifications of the method summaries, the interfaces for the method summaries, all that stuff, and to contribute an abstract but unimplemented API for the abstract interpreter. So so that the inliner has something to call to be able to do the abstract interpretation, but there would be no implementation there in OMR. It would be something left for languages to implement. And the current proposal that I have for how to put it in would be to provide an exit option to optionally enable this new inliner if your language has support for the abstract interpreter, and to make the switch between trivial inlining and this in the optimization manager so that you don't have to special case the whole optimization strategy. And we would look to contribute the abstract interpreter that has been built to the OpenJ9 community so that they could actually continue experiments with this. Follow-on research could be contributed both to OMR and OpenJ9 as appropriate, with as much going into OMR as possible, right? Trying to remove the language dependencies. So
you obviously need to refactor the current abstract interpreter that you have to use this new API if you created it, right, in order to refactor it to contribute it to OMR.
Eric, I believe, has written it with having an abstract API in mind. There's a well-defined set of connections between the abstract interpreter and the inlining mechanism that's actually driving this. So that API exists. The API for doing the recognition of the patterns I don't believe currently exists. That's kind of just tied up in that abstract interpreter. So that would be something to pull out later on. But the actual, here's the set of hook points that you need to call into the abstract interpreter to do this thing. This is what it needs to give back. That exists and can be pulled out from the current implementation.
Do you know what those hook points look like?
I don't have them to hand.
And you mentioned something about replacing the trivial inliner with this in OMR. Is that really the replacement? I mean, do we have a non-trivial inliner in OMR, and is this a better replacement for that?
Well, let's put it this way. The current trivial inliner does the absolute minimum as far as inlining is concerned. There is no large-scale inliner in OMR. All it has is the trivial inliner. So what you can get from the trivial inliner is quite limited. This would be a significant advance on that. For OpenJ9, the equation is a little bit different because they have the multi-target inliner that's heavily tuned for their language.
Yeah, I mean, the trivial inliner on its own has been used in production as well, right?
Yes.
You know, it's used at cold, for example,
yes,
when you can't afford anything more expensive.
Can't afford anything more, yes.
So having the ability to choose between either one, I mean, obviously in the strategy, you can pick this one, and a different cold strategy at the OMR layer, pick the other one.
Right. So if you look at the optimization, the optimization strategies in OMR at the moment have one inlining entry called inlining. If you look at the optimization strategies in OMR, there are two versions of inlining, well, actually three, but we'll leave the third one out. There's one that uses the multi-target inliner, and that's the one that you find in cheap, warm, hot, scorching. And there's one that appears in the cold strategy. I think in OMR it would make sense for both to exist as enumerated optimizations that are available, so like the cheap inliner and the inliner.
Yeah,
and
expensive inliner.
The expensive inliner, for want of a better word. The not cheap inliner, I don't know. Less cheap inliner. I think that depending on your use case, you may wish to replace either of those with something more sophisticated. It's just a question of the time versus benefit trade-off for a particular language as to which one you want to put in a particular slot.
Yeah, that's
what I was asking.
Have the ability to choose.
Yeah. So that's all I kind of put together. So I'll throw it open for questions, debate, rock throwing.
How many optimizations is the Inliner aware of right now?
So the list of optimizations that are currently modeled is this list here. These 5 transformations are what it looks for. And in terms of partial evaluation, it's a subset of all the things that you could do CSV on.
Okay. I guess, is there a plan to make that more exhaustive?
Yeah, well, as I was saying, for the follow-on master's project at the University of Alberta, we want to try modeling something much more sophisticated. The current hope is to model escape analysis, which in the current context is kind of Java specific, but would provide the model for how to deal with sort of heap-based things, which basically the upward propagation and the heap are the 2 things that I sort of view as not being represented in this, and the extension of the work is to figure out from an academic perspective how to make that work.
So if a particular project consuming OMR wants to, they have their own set of language environment specific optimizations, whatever that is, so they can actually add their own, what is the mechanism by which, like these work on the generic OMR optimizations, but how does the language, like the language environment specific optimizations, how can they participate in this?
Well, all you need is an entry in the method summary table, right? So it's just an entry in the method summary table. So there's just a kind and a benefit number. And the only thing that the inlining algorithm actually really cares about is the benefit number, which is what uses to drive its choices, and the constraints. So if you have language-specific optimizations and a language-specific abstract interpreter that's looking for those opportunities, right, you would be able to just inject the opportunity into the method summary table, and away you go, right?
Based on this list, I think there's only 2 that would be relevant in OMR right now anyway, right? The branch folding and the partial evaluation. The other 3 are probably Java-centric.
Depending on how you implemented your language,
Yeah.
So how difficult is it to model an optimization? How much effort is involved?
Depends on the complexity of the optimization.
I was going to ask the same question about the abstract interpreter.
Depends on the complexity of the language.
How much code is that in the Java case, for example? Like, how does that compare to the size of, say, ILGen?
It's significantly smaller than ILGen. Eric, do you have the slot count for that?
Sorry, can you repeat that?
How many lines of code is the abstract interpreter for the Java bytecodes? Just the abstract interpreter.
So just the abstract interpreter for the Java bytecode, it is actually quite large because there are many instructions, but each instruction itself is just a few lines of code.
You said it's context insensitive, right? It's not.
The summary is flow insensitive at the moment. Again, if you want flow sensitive, you can certainly do it.
No, I get it.
There's a lot of different ways that you can expand this to consume more compile time to do better.
Does the current abstract API assume that you're doing a walk over do you have to do a walk over the bytecodes or operations of the method in order to?
No, at the moment I believe it's basically, we would like the method summary table for this method, and go. How you achieve that is entirely up to you.
So it sounds like you could provide a very dumb, simple, quick answer to a question, right?
Yeah.
Provide very much value, and then you can build up to refine that as you.
Right, and the frequency inliner that's being used is basically doing that. It runs the abstract interpreter to consume the compile times, so the compile times are equivalent for evaluation, but it then forgets the answer. Right, basically it does all the math, it computes the answer, and then says it was 1. Right, and then proceeds on that basis.
There wasn't too much difference between the frequency and the analyzer result.
Right. So in DeCapo, like because you're only modeling a very small number of optimizations, the number of those that's going to have a significant impact on performance is not going to be large. If you take a micro benchmark where these particular optimizations happen, you can show very large speed ups in those, because something that you would have not chosen to inline because it was 3 or 4 levels away suddenly becomes something that you are interested in inlining because you see the opportunity. As you model more things, it'll have a greater impact, right? But the frequency is very important. Like, there's always been 2 parts to inlining. One is the frequency and one is the opportunities, or the intangibles, right? And it's certainly managed to do the frequency very well, because otherwise its performance wouldn't be anywhere near what it is, right? We had various points where there were bugs in the implementation where the frequencies weren't being calculated correctly, right? And you ended up in a world of hurt, like, 50%, 60% below in terms of performance, right? There were implementations of this that were in that neighborhood of awfulness when there were mistakes in how the math was being done and the answers weren't right.
So if you don't have good profile information.
So if you don't have good profiling from, pardon?
If you don't have good relative frequency information for things, the algorithm is.
Well, the algorithm will bias towards the things that you've said are good. Yeah. And if everything looks the same, it'll pick something. Right?
It's only as good as the data you give it, surprising.
Yeah.
So this algorithm is, the interpretation is flow insensitive at this time, right?
In the current version, yes.
And is that a general rule of thumb you think will hold as you go forward? Like, let's say you did move to modeling escape analysis. It would probably be too expensive to do a flow-sensitive sort of simulation. At best, you would be doing a flow-insensitive.
Yes. I believe so. And one of the ideas that's being discussed is that we could, in theory, run the flow-insensitive to sort of prune off the least interesting parts of the state space. And if we wanted to try and do better on things that we thought were important, we could then redo flow sensitive.
That's also where a bit of hotness level could come in.
Yeah, certainly.
You could whittle down the candidates of where you want to do flow sensitive analysis and then do them, actually do them at higher level, whereas you don't even do them, say, at 1.
Correct,
right?
correct. So, and this was applied at all op levels, right? So the same naivety was being applied at scorching as it was at hot.
Yeah, you don't have
we don't have that
right now.
We don't have that, but there's certainly scope, and it would be within the architecture and design of what's there to try to do that.
Yeah, obviously, if an opt doesn't even run at that hotness level, there's no point simulating it. Those are things that you can build into the infrastructure.
Yeah, no point simulating it, or you could ignore the entries from the opt table, depending on how much compile time does it take to model it, and how much compile time, or do you just not want to factor the benefit in because it's not something you're going to run, right? You're always free to ignore an entry in the summary table to say, yeah, I'm not going to do that, or I don't believe you.
In general, as a rule of thumb, one that we had followed over the last couple decades is we tried not to simulate a more complex opt from a less complex opt. However, you're in the position of simulating practically everything, or conceivably everything.
If you wish to guide inlining based on that potential transformation.
Yeah. And then it comes down to how complex an opt you inlining as. Maybe it is complicated enough that you would be willing to spend non-trivial amounts of effort simulating a bunch of other opts anyway. Right?
Well, I think one of the bits of intuition that I've at least seen is that the inlining is very important for unlocking the most powerful optimization.
Yeah, it's special. It's different.
It's special because it's an enabler. And because it's an enabler, you have to invest the time for it to enable the right things. If it's too naive, it just bumbles around and sort of makes
it. It's also on the very other end of the spectrum in terms of when it runs versus the only other thing that I think comes close to this, which is the register pressure simulator, which runs very, very late.
Yeah.
It does try to simulate a very complex process, but it's not dependent on all these other ops and all this other stuff.
Yeah.
In some sense, this is harder.
That's also not running on the bytecode.
That's also not running on the bytecode.
Yeah.
I'll ask the evil question.
Yep.
So how do we test it and verify that when we change it, we don't break it?
So I know that Eric has written some unit tests for the actual inlining, the actual algorithm itself. So he has problems and solutions for that.
Those run as standalone.
I believe that they're standalone, aren't they, Eric? The ones that you had?
Yes.
Yeah. Now the inliner itself, well, that has the same kind of testing as the rest of the inliner. The rest of the inliners, right? It's
set a low bar, why don't you?
Run it and see what happens. We haven't invested more than that in it. It's generally been.
But as part of this work, didn't you have some recording facilities for recording the decisions that the inliner was making? And
yeah, so the inlining plan that's produced can be consumed back into the compiler. So if you swipe the inlining table, it can consume that back in and repeat that inlining, basically ignoring all.
So it might be interesting if we could find a way when someone makes a change to the inliner, understanding how those inlining plans change across a set of tests that actually do inlining.
Eric, you wanted to add something?
Thing to do.
Yeah, I think at the moment it might not be working because there has been some changes, but it is something that we can explore on adding back again.
Yeah, well, we can get it working again. It's just things were refactored. We just need to refactor the test to match the implementation.
Yeah.
There were tests.
Just like having a facility so that you can verify that when you make a change to inliner, you have some way of understanding what change you've actually, what the impact of that change has been on these things that we run normally would be nice, even if it's something that a human has to go and review, right? Something that if it's something we could run as part of a pull request, right? When you recognize that someone's changed the inliner, you could request that test be run by it.
Yeah. Eric did have some scripts for doing diffing of inlining plans from verbose logs, so that could be something we could look to contribute at some point.
Yeah, I still have some diffs, like some scripts that do a lot of analysis via the verbose logs and the different, difference in IDTs, difference in inlining plans, and comparing and contrasting and stuff like that. Yeah.
I think Eric spent the best part of the last 2 to 3 months staring at those, figuring out how this thing was working. So.
Right. Well, I figured we could capture some of that expertise when it's being delivered. So we don't have to recover it as a project. Piecemeal.
I guess to build on Mark's evil question.
The evil, why don't you?
One of the challenges we have in serviceability of the JVM in this context is reproducing non-deterministic bugs. And it seems that frequency and the inlining decisions are a very large factor in determining whether you're going to reproduce something or not. So having the ability to, for example, extract the inlining table from a core file and then feed it right back in to make the same decision is a very useful thing.
Yep.
Yeah, I like that too. I mean, it goes back to that enabling question or enabling point that you were making before. The performance is quite sensitive, and what gets presented to the compiler is quite sensitive to what inliner decides to do. So being able to force it to do a consistent thing, like reproduce an error condition, is quite valuable actually, I would think.
Best we have today is to try to inline things.
Well, there's that. Some of the op developers have various other ways that we try to coerce the inliner. We've had some success with that, but it's not being absolute owing to the complexity of the current multi-target inliner. Should you be subject to the joy thereof?
Diplomatically put.
Maybe just to go back to the question that Eunice asked about the complexity. So for something, let's say, like branch folding, how much effort, how much code are we looking at for modeling that? I'm just trying to get a
tens of lines.
Tens of lines.
Yeah.
So modeling branch folding was quite easy. You just in Java bytecode, the arguments are usually placed on the variable array, and so at the beginning of the method, and so we keep track of the variable array and the arguments values, and whether the arguments values have been pushed to the stack, or also if they have been overwritten in the variable array. And so that's just keeping track of the arguments, and that has to be done basically always. But what happens is, just when we are abstractly interpreting a branch or an if statement, well, then we can say, is the value that is a test an argument? And if the answer is yes, then we can say, okay, perfect. We can say, depending on the test, we know that the the branch will fall one way or another one. Perfect. And that's great. And then, again, from the caller, we can inspect the argument and say, okay, the value of the actual argument that we are passing is going to be this one. Does it pass the test in the method summary? If so, then that optimization is going to happen. If not, then it won't happen.
So the branch folding is recognized at the point in the interpreter where you're interpreting the branch. Right? All you're looking at is the arguments, or the things that are being compared, and can we express that as a test of the in terms of the argument? The answer is yes. Then we record the possible choices. If not, we move on. Right? So all of these optimizations are hyper-local in that sense. They're very constrained in the space that they're happening. So the complexity of picking them up is quite simple. If you were to model something much more sophisticated, then yeah, it would take more code.
Okay. Yeah, I just wanted to get a little more of a concrete sense for that. The other thing I was going to ask was, can you talk a bit more about the costs and how those were, how you derived those, and how we differentiate those across different architectures?
So the cost is Java byte codes. It's the number of Java byte codes. It's the same currency that the multi-target inliner in OpenJ9 uses. So its budget is in terms of byte codes. Size. And its notion of size is based on byte codes. And we've set the budget in terms of byte codes as the number of nodes that you're going to allow in the method for purposes of compilation.
And I assume that as there's an API to replace the abstract interpreter, there should be an API to replace that for any OMR language? Yeah,
well, and if there isn't, it wouldn't be hard to add.
Get cost.
Get cost.
Yeah. Kind of related to that is, it's weighing costs versus benefits. Is it assumed that a benefit is expressed in a comparable to number of byte codes number? Is it assumed that the abstract interpreter is translating the benefit into something that trades off against byte codes?
No.
Or how is that?
No, because
how does it decide how much of a byte code is worth how much of a benefit?
There is no notion of that, because what you are saying in running the packing algorithm is that you have a budget in terms of byte codes, and you have a benefit number that is an abstract number. And the solution
never actually compares costs and benefits. It just looks at them independently.
It looks at them independently. It's trying to get the largest total benefit for the given budget of byte codes. So there is no, the really nice property of this is that there isn't a relationship between the benefit and the cost. At the moment, some of the benefit numbers are derived in terms of number of byte codes eliminated, but that's not something that any other part of the algorithm knows anything about.
You don't have to.
No. The goal is just a benefit number. That number is unitless. It's just bigger is better.
Okay, so there wouldn't be a notion of, say, the benefit would be this much if you were able to then apply this optimization that would fold away some expensive opcodes or something like that?
No. So at the moment, so if you think that the transformation is going to save a large amount of compute time, you should be giving it a bigger benefit. Okay. So at the moment, the benefit estimation for the branch folding is based solely on the number of byte codes. But that's just what's implemented in that abstract interpreter. Right. You could add more for calls, or you could add more for whatever, right? Object allocation. And it would bias the inlining to pick to inline those bodies where you're going to eliminate branches that eliminate object allocations and calls, right? And while we don't have the data right now, the final part of Eric's thesis is actually doing a statistical analysis to show that the things that we've incentivized are being incentivized, right? So when we say we want to do branch folding and we want to fold more branches, that's what the inliner is actually doing. That doesn't necessarily translate to a performance benefit because it could be other optimizations that are the determinant on the performance. But he's trying to do the statistical analysis to show, yes, the goal was to increase the number of these, and that is what happened across the board. And the initial results say that, but he's still finishing up all of this statistical analysis on that.
Yeah. Okay, if I sort of understood the main idea back to algorithm, you measure benefit by, basically you see benefit in Holy knowing which arguments were passed in.
So yes.
What about caller knowing something about
He said
Holy?
that's future work.
That's what the next master's student is working on. Yeah. So Kareem and I have discussed ideas for that, but it didn't fit in the scope of what Eric had time to do. Eric's contribution is this notion of abstract interpretation, the notion of modeling these things, the notion of how that fits into the knapsack packing with dependencies algorithm.
You refer to it as propagating up.
Yeah, upward propagation. Yeah.
Other evil question is around documentation.
Right. So we've got 2 talks in terms of PowerPoint slides, as well as there's Eric's master's thesis, which is being written, which describes all of the algorithm in excruciating detail, and we'll have all of the evaluation. There's plans for an academic paper, so a more condensed version.
How about the code itself, like the code that's to be contributed?
I'll defer to Eric on the quality of that. We can set the contribution bar on that as appropriate. I have looked at it. It's not a horrid mess. It's not beautifully documented at the moment, but it's research code.
Well, the bar, I think that we have said for OMR, and the compiler in particular, is at least Doxygen.
Yeah, that can certainly be added as part of the contributing it. If Eric doesn't have time, I'll write it.
No, I can make time for it. Yeah, I'm sure.
Okay. What is your timeline for when you think you might want to make your pull request? Not that it matters.
Go ahead, Eric.
Yeah. So I was thinking about starting as soon as possible in the sense of just where the the new inlining class should fit in. And after contributing that, the contribution of the abstract interpreter, as you mentioned, or someone else in the room mentioned, still needs to be polished in terms of code, but it's just a matter of polishing a little bit and pushing it, and that can be done, I don't know, maybe like once a week, submit a pull request and continue iterating over that. So I think in terms of readiness, I think it's ready. It certainly could use some code reviews and a little bit of polishing, but other than that, yeah, I'm excited to contribute this as soon as possible.
So Eric's timeline for finishing up his thesis work is by the end of April, for him to be completely done. The code is close to being ready. I haven't done code reviews on it myself. I've certainly looked at parts of it and I was able to find my way around, but I haven't done a comprehensive review. I can certainly do that before the pull request is opened up if people would like, and then the pull request can be opened up or we can just open it up for open slather. And basically, I think it will be a case that we're looking, both of us would be looking for feedback from everybody about what needs to change. There'll be a finite limit on the amount of changes that can be done, obviously, because it's one person and a fixed amount of time, but we'll certainly try to accommodate anything that needs to be accommodated. there's already been quite extensive evaluation in terms of the compile time and the memory and that kind of thing. So from that perspective, it's pretty tight. But in terms of some of the RAS and some of that other stuff, there's probably room for improvement. We can look at that.
So that propagation up again, like back to that, it's sort of like prerequisite. You're not going to enable without it, or you might be.
The current inliner works without the upward propagation, and the proposal for the contribution would be to contribute it without the upward propagation.
But don't we then give more weight to kind of that first benefit? Because sometimes
you just don't even see the benefits in the other cases. So yes, you are biased to certain
You're
kinds.
biased. You're basically
you are biased.
Right now, yeah.
I wouldn't say otherwise.
Like there's some call, for example, just does a load, and you say, oh, there is no benefit, but the caller can do like PRE on it and to take it out of the loop. You know what I mean? Like,
yep.
Benefit can be pretty big, but you're biased towards.
Yep.
Calling.
Yep. But the current trivial inliner wouldn't even find that, so.
That's true, yeah.
So I'm not going to claim that it solves the world's problems. However, I think that my personal opinion is that it is a significant improvement over the current state of affairs and has significant scope for being enhanced in ways that are understandable, maintainable, and extensible, unlike the current inliners that are candidates for inclusion in OMR beyond the trivial inliner.
But we do some peaking right now.
The peaking is only in the multi-target inliner. It's Java specific, and it's generally disabled pretty much at the moment because of HCR. And the peaking is more to see the size of things. You can do a little bit of a type propagation. It doesn't do full value propagation constraints. It's quite limited. And it's quite expensive because it does tree gen, right? The reason that we didn't do tree generation for this abstract interpreter is because of that cost. Now, for OMR, it may make a lot of sense to build the interpreter for the nodes, because being able to run an interpreter over the nodes, even with the cost of generating the nodes, means that all languages would get one by default, and if you want a better one, then you can create your language-specific one. It's just to be able to evaluate this in a large-scale context and in a way comparable to the current inliners that are available as amongst OMR and OpenJ9. It was done with the bytecodes because of the evaluation context in Java. I don't think it would be a huge undertaking to write that abstract interpreter.
It depends on the optimizations.
Right, but to get it to the same state that the Java one is, I think it would be a relatively straightforward undertaking, because in most cases it's just push a value, pop a value, constrain a range, you're done.
Yep.
Now, as more things are added, you need to add more things to it, but what you put in is what you get out, right?
Yep.
Any other questions for Andrew or Eric? Okay, well, we look forward to seeing some code.
Okay.
Reviewing that, so thank you.
All right. Well, Eric and I will work together to get some pull requests opened.
Cool.
Thanks, Eric.
Yeah. Thanks, Andrew. Yeah.
Thanks, Eric.